All right, folks, let's take some notes on 6.9 extraneous solutions. Extraneous. This word is kind of like Wednesday when you spell it. I think Wednesday to spell Wednesday right. Extraneous. You can think extra, neo, us. Think of this like extra solutions, solutions that come from the solving process that we don't actually need, that don't actually work. So for a solution to be valid, it must make the equation true. If you substitute a solution back into the original problem and it does not make the equation true, it is an extraneous solution, provided that you found it by solving properly. This is not because we made an algebra mistake, but because we did all the algebra right. The algebra told us there's this answer, and when I plug it back in, the answer doesn't work. If you fail to solve properly and you get a wrong answer, we wouldn't necessarily call that an extraneous solution. It's just an incorrect answer, right? So there's difference between messing up the algebra and not getting the right answer because of that and finding an extraneous solution. Now, extraneous solutions happen when you start with a function with a restricted domain. Restricted domain. When you change it, when we're in the solving process and we change two functions with an unrestricted domain or a larger domain. For example, we start with a square root function in our equation, which has a restricted domain, x must be greater than or equal to 0, and then we square both sides to get rid of that square root and end up with a quadratic. That has all real numbers in its domain. So we can potentially catch extras when we expand the scope of x values we're looking at. So when we want to identify extraneous solutions, we will take that value, plug it back into the very original equation, and simplify on both sides and find out if they are equal, right? Does it make the left side equal to the right side? We do not use inverse operations to test if a solution is valid, okay? We don't work backwards from the end. That's just going to walk us right back through the same algebra we did. All right, a function is undefined when dividing by 0. So these functions will have restricted values. These are restricted values, values that when we plug in, they cause an attempt to divide by 0. So if you solve an equation with involving an inverse variation function, and you get that the answer is the restricted value, you know that that cannot be a solution. So it's an example of an extraneous solution. For example, number 7, our restricted value is the location of the vertical asymptote, the value that would cause an issue for the domain. The value that is not included in the domain here is -1, because that makes the denominator here 0. This function is shifted left 1 unit, so we know the vertical asymptote is at x equals -1 instead of 0. That's our restricted value. No solutions are allowed to be x equals -1. So if we encounter some solving, our first example is a square root example. We'll start by solving like normally. We'll square both sides since the square root is by itself. X minus 2 quantity squared, we need to expand and distribute. So we have x squared minus 4x plus 4 equals x plus 4. It's a quadratic, so we need to get it equal to 0. Subtract x from both sides, subtract 4 from both sides, and we end up with x squared minus 5x equals 0. Because this is just a binomial, all I need to do is factor out the greatest common factor. This is factored form. You should show your factored form every single time. And then set each factor equal to 0 and solve. The first one is just x equals 0. The second one, I have to isolate x to get x equals 5. Then we need to check to see if either of those are extraneous. So think about the left side. X minus 2 would be if x equals 5, then 5 minus 2 equals 3. This is the left, If we check the right side was the square root of x plus 4. Remember, we're going all the way back to the very original function, not the squared version, right? So if x equals 5 here, then we have the square root of 5 plus 4, that's 9, square root of 9, so that's 3. Since 3 equals 3, we're good there. Now let's check when x equals 0. X minus 2, where x equals 0, is negative 2. 0 minus 2 equals negative 2. On the right, the square root of 0 plus 4 is the square root of 4, which is positive 2. Negative 2 does not equal positive 2, so x equals 0 is extraneous. So I'm going to keep 5 because it's valid. It causes the left side to equal 3 and the right side to equal 3, so it's a true statement. But 0 is extraneous, and I'll label it extra neo us. Extraneous. I'm not going to put it in a box. I leave it in my work, but I'm going to label it extraneous and put the valid solution in a box to indicate it does work. And 0, though algebraically it shows up, is not a valid solution. Example 2. I have a fraction equal to a fraction, so I'm going to cross multiply. Before I even bother doing that, I'm going to find the restricted value. Both of these fractions have a restricted value of x equals 3, because if I plug in 3 to either of those denominators, it's going to cause division by 0. So if I'm not looking too closely at this, I'm just going to go ahead and start cross multiplying. But I do want you to take a moment to think, are these two things ever going to be equal? If their denominators are the same and their numerators are not the same, and the only thing that can change is those denominators, but the denominators will always change in the same way, are 2 of this thing and 1 of this thing going to be equal ever? Think about that before we get into it. So when I actually cross multiply and start solving, I have 2x minus 6 equals x minus 3. If I add 6 to both sides and subtract x from both sides, I get x equals 3. But since the restricted value is 3, there are no valid solutions because x equals 3 is extraneous. It is this restricted value, so it cannot be an answer, right? The only thing that I could plug into both of those sides of the equations to make the equations match would be the value that makes both of them not exist. And they can't be equal where they don't exist. So that is x equals 3 is where they don't exist. If that's the only algebraic thing that makes the expressions the same, then there are no valid solutions, and we call x equals 3 extraneous. Last but not least, I'm going to make the right side of this equation a fraction by putting it over 1. I have x times 4x minus 7 and 2 times 1. That is 4x squared minus 7x equals 2. And finally, since that's a quadratic, let's get it equal to 0 and think about factoring or using any of our other methods to solve, right? We could factor this and say where is what multiplies to a times c and adds to b. A times c would be 4 times negative 2. That's negative 8. And what adds to negative 7? But if you do that method, you either need to factor by grouping or think about your box method. I'm going to do the box just to remind us of it. We have 4x squared and negative 2. A times c is negative 8, so we want to multiply to negative 8 and add to negative 7. So I'm thinking 1 and 7. And which one do I need to make negative? Well, I want them to add, 1 and 8 to multiply to negative 8. And I want them to add to negative 7, so let's make it negative 8x and positive 1x. That adds to negative 7x and multiplies to negative 8. There we go. So when we find the dimensions of this box, we think about our greatest common factors. This should be a 4x. X times x, 4x is 4x squared, negative 2 times 4x, negative 8x. When nothing comes out, a 1 comes out. 1 times negative 2, 1 times x, that works. Okay, so our factored form is 4x plus 1 times x minus 2 equals 0. So x equals negative 1/4 and x equals positive 2. Remember, we set these factors equal to 0 and solve, subtract 1, divide by 4, and add 2 to both sides to get negative 1/4 and positive 2. The restricted value here is what makes the denominator 0. So the restricted value is x equals 0. Since neither of these are x equals 0, then both are valid. So we can say valid solutions. The only restriction is x equals 0, and so there are no extraneous solutions. Both solutions work, negative 1/4 and positive 2. We still need to know how to solve those quadratic equations.